Yeah, the name of the design which follows now is FRA. The name of this design, FRA design, which comes from the word frequency response approach. Frequency response approach. I find this expression in literature. Yeah? In German we say FKL-Verfahren, Frequenzkennlinienverfahren. In both cases, the frequency response expressed by the Bode plot or the Frequenzkennlinie is the Bode plot. So, German, if you look into books, yeah, if you look into books, then you can find the FKL-Verfahren. Okay, before this used the Nyquist stability criterion. Before we start into the design steps, I want to show you in chapter 5.1 that there are some objectives of the design, some goals of the design. Objectives. And each goal is now investigable with some indicators. The FRA design offers the possibility to get indicators so that you can see very in the beginning if your controller design in the end will be good or not. Yeah, these indicators are very helpful in this design process. So I will show you these indicators. Yeah, what objectives are important in a controller design? I show you 5 objectives. First, second, third, fourth, fifth. The first objective is, of course, a loop must be stable. Yeah? The most important objective of a closed loop system is that the closed loop system is stable, otherwise you cannot use it. Yeah, and the indicator is, we have learned, is a phase margin. Phase margin must be positive. But a stable system is not a good or a sufficient condition. It is a necessary condition, but not sufficient. You need more objectives to get a good loop. Yeah. The next is the loop can be stable, but what happens if you are very near to the stability limit? Then we have seen in some cases that you have oscillations. Yeah, the damping is bad. You need a well-damped system. And the interesting thing is the phase margin is also a good parameter for the damping. If the phase margin is 0, then you have zero damping. If the phase margin is small, then you have bad damping. And the larger the phase margin, the better the damping. So, in typical systems, we have, say, 40 to 70 degree phase margin values. A typical default value, starting value, default is phase margin is 60 degree. So typical value, you start normally with 60 degree phase margin design and then make adaptations if you are ready to make the damping a little bit higher or smaller, but 60 degrees is a good value. Okay, but a stable and a well-damped loop could not also be a bad loop. So you need more conditions to have a loop for which the user is happy. Yeah. So the next is the speed. You mostly want to have a fast speed. if you change your desired value, you expect that the controlled value follow as fast as possible. Yeah, so we need fast loops, and yeah, one indicator you will see is the crossover frequency. The value of the crossover frequency indicates the speed. I will show you in the next steps with some additional information that the Tmax value of the RSR, the reference step response, is approximately calculatable with 4 divided by crossover frequency. So the larger this value, the smaller is my Tmax value, and the smaller is the settling time. Yeah, settling time is in the near of Tmax, and it's the inverse of the crossover frequency. And with this thumb rule, we can say, okay, we have an indicator for the speed of the closed loop system. Note that omega d is the value at the open loop curve. Yeah, and we predict the reaction of the closed loop system. But a stable, well-damped, fast loop could also be a bad loop, because it could have high control errors. Yeah, the accuracy is also important, and a very good accuracy indicator is, of course, the control difference. If I wait long enough for the oscillations come to rest, the control difference for large times, then is an indicator. If I can calculate this control difference with values coming out of the open loop Bode plot, which is available for all these investigations, then this is a very good help. And there is already an equation which is 1 divided by, I will show you in some next chapters, 1 divided by 1 plus open loop gain at omega 0, DC gain. 1 divided by 1 plus DC gain. If f open loop at omega is 0 is the DC gain of open loop. So if this is very large, this is very small. To make the open loop gain for DC as large as possible, then this is as small as possible. Yeah, so these are 4 indicators for the most important parameters. And the last parameter is, we of course want to have a cheap one, but what is cheap depends on application. We in this lecture can of course not tell anything about which is cost effective. In a military system, of course, you can spend more money as in a system for home use. Yeah? So cheap depends very much on the application. So we can only tell something about the 4 technical parameters, and if stable, well-damped, fast and accurate loop can be sold, then be happy. If this fits to the price of the user, then this maybe can become a good product. Now the point 1 and point 2 indicators, the phase margin, is just explained in the Nyquist criteria. So I don't want to spend more information about this, but the indicator of 3 and 4 has to be explained a little bit more deeply. So explanation. Indicator 3 for speed indicator. Okay, how can we find out that the 4 over omega d is a good estimation for Tmax? I will show you this very quickly in the following step. For this information, we look again on our loop system, which has the open loop function known as Bode plot, negative feedback, and we assume that we apply a reference unit step function at the input. So we can say here this is the sigma of t at the input. Then we have the so-called R is R, the reference step response, the unit reference step response at the output. This is h of t. And this h of t, if we draw this, h has a final value. And if we have a well-damped system, looks like this. So in a well-damped system, the peak of the overshoot touches the tolerance range upper limit, and we have defined that we have this time value for the first maximum we have called Tm or Tmax. Question is, can we estimate or calculate the Tmax value if only the Bode plot of the open loop is given? For this, note that we have discussed in chapter 3.9 following situation. Given magnitude curve of the open loop with the main behavior described in the beginning of this chapter, we have the crossover frequency omega d, and we have discussed in chapter 3.9 C 3.9 that if the gain is large, closed loop is 0. If the gain is small, closed loop is identical to open loop. And in the range of omega d, the phase defines if we have resonant effect or not. If we assume that we have a well-damped system, then we can say, okay, closed loop systems with well-damping works like this. So this is if yeah, come if well damped. So there is no resonant effect. Now, if there is a resonant effect, of course, then number 2 is not true. So the closed loop Bode plot magnitude curve looks like this curve. And if we now compare this with known behaviors, then you can very easily see in the workbook page 16 that this fits to the PT2 red curve fits to PT2 step response. Let's have a quick look in workbook. Here you see this behavior of the magnitude curve is the PT2 magnitude curve. There could be a resonant effect. If the damping is well, then there is no resonant effect. But you see the corner frequency here defines the natural frequency parameter of a PT2. This one appears in the transfer function here. So the omega naught frequency is the corner frequency. Is the corner frequency of the PT2. So this can be used to say, okay, corner frequency omega naught is exactly at that position where we have defined our crossover frequency. So this is a good estimation for the crossover frequency. Note that in PT2 we have an equation for the Tmax. Tmax was P divided by omega naught divided by 1 minus d squared. So, you see here with this corner frequency we have a good estimation for omega d, and what I have promised, omega d is inverse proportional to Tmax. This is really true, and the factor here, pi divided by square root 1 minus d squared, can also be estimated with following trick. We can say, okay, this is 3.14 and this is omega d, and how large is d? If we have a well-damped system, we can say, okay, d is in the order of 0.7, and if we put this into this equation, 1 minus 0.7 squared, we get the following value. Now I have to correct myself, not 0.7. If I calculate phase margin value 60 degree, this can be converted in a second order system into a damping factor of 0.61. With an equation you can find on page 33. There you can find for second order closed loop systems a very clear ratio between phase margin and damping factor. And if we add this into my square root function, 0.61 squared, that is square root, then we get 3.96 divided by omega d. And of course, because this is just our rounding, we can say, okay, this is 4 divided by omega d. Very simple. Tmax can be estimated by 4 divided by omega d, and this is a very good speed indicator. So make the crossover frequency as high as possible. This gives very small reaction times, settling times, make your system fast. The larger omega d, the faster the system. The larger omega d, the larger speed. So this is one main information. Omega d as a speed indicator is helping in our design procedure very much. So now to indicator 4, last step, explanation. Indicator for accuracy. I do the same. I apply the unit step function to my closed loop system with given open loop function, added with negative feedback. I apply the unit step function. Here, of course, you have the reference step response, but we don't have interested in reference step response. We are interested now, that is x, for the control difference. We want to have the response on this signal of the control difference. And of course, then for large values of the time. That is what I want to calculate. Here you see, I want to show you now why this value is identical to this value. Okay, we can do this in the following way. We can say, okay, the xd for large times can be calculated with Laplace transformation with the following limit value of the frequency response. That is limit p goes to 0 of what? We now use the limit value, the final value theorem, the final value theorem of Laplace transformation, which can be written as the limit of the time function xt for large times is a limit for the frequency function p times xd of p if p goes to 0. Yeah, that is the final value theorem of Laplace transformation. Final value theorem of Laplace. Maybe you have heard this. If not, look into mathematical books and you can find it. What is this? This is the frequency function of this. So we can say x of t corresponds to xd of p. And this should be the unit reference, is the unit step response of the signal. So we now calculate an expression for this xd of p. xd of p is the response of this loop system, of this signal, where we can say, okay, this is the response of a step function. It's 1 over p. So this is the step multiplied with the function which produces this signal if this is the input. This is the output, this is the input. Note for them who cannot see this in one glance, we just redraw this signal block diagram in this way so that you can see this. I redraw this plane in this way. Note this is x, this is xd, this is of course w. Yeah, this signal block diagram and this are identical, just redrawn so that you can see, okay, input, if this is the input, this is the output, this is xd of p is the f, this is, let's call it fxd, and fxd, the transfer function, is the output xd of p divided by the input w of p. And we can calculate this fxd of p by resolving or simplifying this signal block diagram. Simplifying rule, chapter 2, is 1 divided by 1 plus all functions in the loop is f(o) of p. That means if I now put this thing in this expression, that we can calculate xd of p as 1 over p step function multiplied with transfer function is 1 divided by 1 plus transfer function of the open loop of p. So that is the frequency function of my control error. Now I want to have the limit value of the control error here. I have calculated now this function here. Now I put this function there and execute the limit value, and you see xd of t goes to infinity is limit value p goes to 0 of p times xd of p is 1 over p multiplied with 1 divided by 1 plus fo of p. And now you see here we have a reduction and delete of the p factors, and here just replace a p with a 0 value, and that what I want to prove is my control error for large times is calculatable exactly with the open loop gain at p0, which is a DC case. This is a DC gain of open loop. So make the DC gain large. This caused the error to be small. Best case, if open loop goes to infinity, in this case we have a control error which is 0. So that's what you have to do. Try to set the DC gain to infinity. Is it possible? Is possible. I show you page 16. Yes, it is possible. You would just look for an integrator. Integrator is a transfer function, constant value over p. If p goes to 0, this is infinity. Here's a p in the denominator. A naked p in the denominator caused exactly this case. So here in IT1, DC gain infinity, PI, DC gain infinity, PID, DC gain infinity, PIDT1, DC gain infinity. So in any case where the name of your controller has an I, you have exactly this case, and this is proven, yes, if a controller or process carries an integrator, So if you want to have 0 control error, work with a PI controller, work with a PIDT1 controller, or if the process, look for open loop. We talk about open loop. Where is my open loop? If the process has an integrator, the reference behavior doesn't need an integrator here. One integrator in the open loop is enough for the reference control error. Yeah, is 0. So very important. This is the indicator for control error. Note this is a control error in reference case, not in disturbance case. Yeah. Note we have calculated the control error in the case of the, was ist denn das hier alles? We have calculated this control error if this is a unit step function. That's a reference step response. Note only valid for reference behavior. For disturbance behavior, see chapter 5 later. Yeah, in project 4. Yeah, for disturbance behavior. See project 4. Project 3, which comes now, is a system where the process has a series of PT1s. In project 4, we have a system where the process itself is an integrator, and then we have to discuss disturbance behavior. Okay, so far this is the end of now video number 49.